Hello, my name is Dr. Ambikesh Jayal, and I have created this brief presentation to show you some of the concepts in digital signal processing, namely the discrete Fourier transform and filtering. I'm going to show you the code, which is this, and the output, which is this. And as you can see in the output, there are three plots. Um, this is the first one, this is the second one, and this is the third one. The first plot is the plot of the original signal. The second plot is the plot of frequencies present in the signal calculated using discrete Fourier transform. And the third signal is the plot of frequencies in the signal after it has been filtered using a low pass filter. Okay. And as you will note in these plots, so the first plot is time domain, obviously. The second plot is contains frequency components of 2 Hertz and 4 Hertz. And the third plot contains just the frequency component of 2 Hertz. So in the third plot, which is a filtered signal, the frequency component of 4 Hertz has been eliminated. Okay, now I'll switch on to the code. So this is the code. The code is on GitHub, so you all can access it. I'll put the link in the description of the video. Um, I'll just speak about some of the key elements of the code. So the first one is sampling frequency. And I have set the sampling frequency as 10. The reason being, my original signal is on line number 20. And the original signal, as you can see, it contains two frequencies. One is 2 Hertz and one is 4 Hertz. So 2 pi t is the standard term. And then the other term is the frequency present in the signal. So one is a 4 Hertz and one is the 2 Hertz. So basically this signal Y consists of two sine waves. And the first frequency being 2 Hertz, second frequency being 4 Hertz. And because the maximum frequency present in my signal Y is 4 Hertz, so as per the Nyquist theorem, the sampling rate should be at least double of the maximum frequency, so at least 8 or more. So I've set it as 10. And then on line number 23, I use a low pass filter. And this low pass filter basically filters out any frequency component which is more than 3 Hertz. So it allows any frequency which is less than 3 Hertz to pass through, but it stops any frequencies which is more than 3 Hertz. So what we are expecting here is in the Y filtered signal, because we have applied a low pass filter, the frequency component which is 4 Hertz should not be present in the Y filtered signal, in the filtered signal, because it should have been filtered out, because 4 Hertz is more than the 3 Hertz. Okay, so what I'll do is I'll just plot the original signal in time domain, then the original signal with frequency components, and the filtered signal. So these are the plots. I'll go through it in a second, but what I have done is I have written a function called draw Fourier transform, and this function basically takes three parameters. One is the sampling frequency, one is the signal, and one is the title of the plot. And then it first calculates it computes the discrete Fourier transform using the FFT function, which takes the signal and returns YFFT. And this YFFT contains the information about the frequency component of present in the signal. Then I calculate the number of elements in the signal using numL function. And then I calculate a variable f, which will represent the frequencies that corresponds to values in YFFT. And then I basically plot the f, and in order to output values from the FFT function, which is this one. So YFFT is a complex numbers. It has got a real part and a complex part. Complex is complex components represented by I, which is square root of -1. So to plot their magnitude, you could use the ABS function on YFFT. So that's what I have done. So I've used the plot function giving first the x-axis, which is f, and along the y-axis I want the magnitude to be plotted, and then this is the title. Okay, so then this is the way I've done the plotting. So so there are three plots. This is my first plot, line 30 to 36. Line 37 to 40 is my second plot, and line 42 to 46 is my third plot. So the first plot, which is line 30 to 36, I have effectively plotted the time domain plot view of the signal. So this is my original signal. And I'll just switch on to the plot. So this is my first plot. You can see it's a time domain signal. The second plot, which is here, which is line number 37 to 40. I have used the function draw Fourier transform, which I have written, and I have passed it the sampling frequency and the signal, the original signal, and the signal is this. And as you can see, what has been done here is the discrete Fourier transform has been calculated of the original signal, which is this, and then it extracts the frequencies present in the signal, and you can see the major frequencies present in the signal is 2 Hertz, which is, if I just hover over it, you can see the value 1.99, almost 2. And if I hover over here, so 3.98, which is approximately 4 Hertz. So there are two dominating frequencies present in my signal. In the third plot, which is this, I have used the low pass filter on this signal and filtered out any frequencies more than 3 Hertz, and hence the 4 Hertz frequency is missing from my filtered signal. So this is the code for it. So that's the third plot, and effectively I have the custom function which I have written, draw Fourier transform. I have passed the Y filtered parameter, which is a filtered signal here. Okay, and so you can see in the demo that the low pass filter has eliminated the signal at 4 Hertz. So now it just consists of a signal with 2 Hertz. Okay, thanks very much for viewing the presentation. The code and this output file as a JPEG file is present has been uploaded in GitHub. Thanks again. Thank you.